And now let's try to solve a question based on this concept. So here we go. Let's read. There is a disk of mass m and radius r which is rolling without slipping from rest down an inclined plane. The angle of the incline is theta. Moment of inertia of the disk is given. We need to find the value of linear acceleration as well as the net torque. We have already derived the expression for linear acceleration. So in MCQ questions, you can directly apply that formula. But let's say if this question comes in the form of a descriptive question, then please do not apply that formula. We'll have to go step by step. We'll apply F net is equal to ma. Then we will apply the net torque is I alpha. And the third equation, remember, is A is equal to R alpha. So in a descriptive question, of course, you will be marked on the steps, but this is an MCQ question, so we can directly apply that acceleration expression, which is equal to, let me write, g sine theta was the numerator divided by the denominator was 1 plus I upon mr square, where I is the moment of inertia, which is given in the question as mr square by 2. So if we replace I with mr square by 2, the expression will become g sine theta is in the numerator. We'll get 1 plus 1 by 2 in the denominator. Now the denominator 1 plus 1 by 2 is nothing but 3 by 2. So let's write g sine theta divided by 3 by 2. Now this 2 can go in the numerator. So the final expression for the acceleration, let me write on the top, it will be 2 by 3 g sine theta, which means now if you look at the options, it is either option A or option B. C and D are definitely out. Now we need to figure out the net torque. How do we do that? We have already discussed this. To identify the net torque, we need to identify how many forces are acting on the sphere. So let me repeat. The first force is mg, the weight of the object, weight of the sphere. Then the normal reaction, which is perpendicular to the incline. And since the incline is rough, so friction will act up the incline as shown. Now coming to the torque, torque due to mg and torque due to n will be 0 because mg and n, both these forces are passing through the center of the sphere. And center of the sphere is also the axis of rotation. And the concept was if the force passes through the axis of rotation, then the torque of that force about that axis will be 0. So torque due to N and mg, they are 0, but the torque due to friction, we just use Rf sine theta. So like we earlier discussed, torque due to friction will be Fr sine 90. Sine 90 is 1. So the torque due to friction will be just F into R. And if you look at the options, option A has friction F. This expression, capital F with a suffix of F, this actually represents the force of friction. So we are multiplying friction with R. That is the torque due to friction. And that is why answer is A. A is the answer to this question. So this was an MCQ question where we applied the expression directly. But as I told you, please do not apply the expression in a descriptive question. So now let me show you that type of descriptive question which is based on this concept. So here we go. Please read this question very carefully. Take your time. Try to solve this question on your own first, and only then please look at the video solution. So here we have been given a hoop of mass m, radius r, and moment of inertia. It rests on a rough plane which is inclined at an angle theta to the horizontal. It is released so that the hoop gains linear and angular acceleration by rolling without slipping. Now, this term rolling without slipping has a very important role to play, which I will explain in a little while. But for now, let's start with part A. On this diagram, draw and label the forces acting on the hoop. So this question is easy. The first force acting on the hoop will be the weight of this hoop, which is mg acting downwards. And since the hoop is placed on an inclined plane, which means the hoop is in contact with the surface, the hoop is going to experience normal reaction. The direction of this normal reaction will be perpendicular to the incline, and this angle will be 90 degrees. And the third force acting on the hoop will be friction, since it is mentioned that the incline is rough, and also it is mentioned angular acceleration of the hoop is there. Now, angular acceleration will only come into the picture if the incline or the surface is rough. Hence, the third force acting on this hoop will be friction, and the direction is up the incline. And that's how we answer the part A. Coming to part B, we need to figure out the expression for linear acceleration of the hoop. To solve this question, all we need to do is just apply the Newton's second law for linear motion first and then for rotational motion. For linear motion, the formula is F net is equal to ma, and for rotational motion, we are going to use torque net is equal to I alpha. And then we use the expression which connects linear acceleration with angular acceleration, which is A is equal to R alpha. So let's start with F net is equal to ma. Remember the concept, we need to apply this equation F net is equal to ma along the direction of acceleration. In this case, the hoop is going to have a linear acceleration along the incline, so in this direction. In order to find the net force along the incline, we will break the mg into components. Since the angle of the incline theta is given, so the component of mg which is perpendicular to the incline will be mg cos theta, and the other component of mg which is parallel to the incline will be mg sin theta. Now the net force along the incline will be mg sin theta minus f, because mg sin theta is acting down the plane, friction is acting up the plane, the hoop is rolling down the plane. That is why mg sin theta is greater than friction. So the net force will be mg sin theta minus friction. That will be equal to m into a. And then we come to the second equation, torque net is equal to I alpha. In the free body diagram, we saw there are three forces acting on the hoop: normal reaction, friction, and mg. So how to identify the torque? We already know the formula, torque is equal to Rf sin theta, but the normal reaction and mg, both of these forces are passing through the center of the hoop. And remember the logic, whenever any force passes through the axis of rotation, torque of those forces about the axis is equal to 0, which means torque of normal reaction is 0, torque of mg is 0. For friction, we can use Rf sin theta. So torque for friction will be friction F multiplied by R, where R is the radius of the hoop. Hence, the total torque will be just the torque due to friction, which is F into R, and that will be equal to I into alpha. And then we come to the last expression, A is equal to R alpha. From here, what we'll do, let's make alpha as the subject so that we can replace in this equation. So over here, if we make alpha as the subject, we will get A upon R. And then if we replace this alpha over here, so the expression will become this, Fr is equal to I A upon R. And now in the question stem, it is mentioned that the moment of inertia of the hoop is mr square. So let's write down I is equal to mr square in this expression. So our expression becomes this. And now if you simplify this equation, all r's will get cancelled out, and eventually we will just get F is equal to ma. So friction is the product of mass and the linear acceleration. Now back to the question, we are supposed to find the acceleration expression. So in this equation, we can make A as the subject. But before we do that, we will replace the friction with m into A. So mg sin theta minus ma is equal to ma. Now we will make A as the subject. So this negative ma, we can shift this to the right hand side of the equal symbol. So we will get mg sin theta is equal to ma plus ma, which is 2ma. And from here, if we make acceleration as the subject, we will get g sin theta upon 2, as m will get cancelled from left and right. And this is the expression which the question wanted us to derive. Linear acceleration of the hoop will be g sine theta by 2. Now, coming to the part C, we have to find the linear acceleration of the hoop when theta is equal to 20 degrees. We already have derived the expression for acceleration, which is g sine theta by 2. So let's put all the values in. G is 9.8 multiplied by sine of the angle 20 divided by 2. And if we simplify this expression, we will get acceleration as 1.68. And since it is acceleration, the unit will be meters per second square. And that is how we solve the first three parts of this question. All the first three parts of these questions are extremely important in order to understand the concepts of rigid body mechanics. Now we have two parts still to go, D and E. That will involve another concept which I'm going to explain in a little while. But before that, let me present those questions. Let's see how those questions look like. So here we go. The question stem is the same. Part D is state the relationship between the force of friction and the angle of incline. So we need the relation between friction acting on the hoop and the angle of incline theta. Part E, the angle of the incline is slowly increased from 0. So the value of theta keeps on increasing. So this incline will become steeper and steeper. We need to determine the angle in terms of coefficient of friction at which the hoop will begin to slip. At this point, I'll need to explain what this rolling without slipping concept actually is. And then we will understand what is the impact of the angle of incline on the ability of the hoop to roll either without slipping or with slipping. Let's understand this in detail. The next topic is impact of angle of incline on the acceleration of the objects. In the forces chapter, when we were learning about friction, we have partially done this. And that topic was friction on a box kept on an inclined plane. So have a look at these two diagrams. We have an inclined plane having different angles of inclinations. This is a smaller theta. This is a bigger theta. And the question is, what will be the amount of friction, magnitude of friction acting on the blocks in situations where theta is different? We are going to understand all of this in detail. And after that, we will come to the topic which is more relevant for this chapter, rigid body mechanics. And that is friction on a sphere which is moving on an inclined plane. And of course, the inclined plane will be rough as we want the sphere to have linear acceleration as well as angular acceleration. So the sphere also needs to rotate apart from the linear motion. And through this, we are going to understand what is rolling without slipping and rolling with slipping. Let's start with the first topic, friction on the box kept on an inclined plane.